The sun casts its last rays onto a formidable structure, the towering Ponte Duca d'Aosta bridge in Turin, Italy. Below, workers secured explosives to ancient concrete, their breaths misting in the cool evening air, preparing for an operation that would either topple the 1910 edifice or witness it stand defiantly. It had endured wars, floods, and the slow march of time, yet today's planned demolition is no simple task. As the countdown begins, the massive structure that weighs over 20,000 tons sits firmly on its foundations, unyielding, almost mocking their efforts. It begs one singular question: how do architects and engineers design buildings that can withstand more than anyone anticipated, even to the point of resisting destruction? In this countdown of resilience, we'll explore 7 astonishing structures that not only stood the test of time but also resisted their demolition attempts far beyond what engineers thought possible. By the end, you'll comprehend the surprising mechanisms behind their formidable endurance. We begin our countdown with a forgotten giant from Wales, the Pontypridd Viaduct. This impressive example of Victorian engineering stretches over 170 meters across the River Taff, supported on 10 lofty arches. In September 2015, it faced the first of 3 demolition attempts. Workers prepared charges, envisioning the grand collapse of this historic structure. Yet when the dust settled, the viaduct remained intact. An investigation revealed that its solid stone piers, made of limestone, were more resilient than expected, absorbing the forces of demolition without yielding. It's not just the materials but the craftsmanship that contributes to its endurance. The builders utilized a technique known as arch action. The weight of the structure directs downward forces into the piers, allowing it to resist significant loads. Engineers estimated that each arch could carry over 100 tons. While it was built to last, it's become clear that this Victorian marvel is something of a stubborn giant that wouldn't crumble easily, letting us reassess what we consider demolition ready. As we move up the countdown, we reach our 6th entry, the Kingdome Stadium in Seattle, Washington. Completed in 1976, this indoor arena served as the home for the Seattle Seahawks and the Seattle Mariners. When the time came to demolish it in 2000, engineers were initially confident. Over 490,000 pounds of explosives were strategically placed, ready to bring the iconic dome crashing down. However, after the explosion, the structure remained partially upright. Its reinforced concrete failed to yield the final collapse that had been envisioned. The design, particularly its Teflon-coated, composite material, was more resilient than anticipated. The explosive force only managed to scuff its surface, like a kid playing tag with a rubber ball. The stadium's roof was engineered to handle immense wind loads, able to withstand forces of up to 100 miles per hour. Ultimately, it was a second wave of explosives that finally brought it down completely, one of the largest demolitions ever attempted, serving as a stark reminder that sometimes structures refuse to comply with our expectations. Next on our list are the German U-boat pens in Bordeaux, built during World War II. Entering these structures elicits a sense of claustrophobia. They are indeed immense bunkers, designed to withstand aerial bombardments and secure submarines. The roof is up to 1 meter thick, composed of ferroconcrete, a mixture of concrete reinforced with iron and steel. When Allied forces attempted to destroy these formidable pens, over 500 bombs were dropped with little effect. The reinforced roofs, designed to take stratospheric impacts, absorbed the explosive forces like a sponge under pressure. Some estimates suggested the materials could withstand multiple impacts and still remain structurally sound. Today, the remains of these pens stand as a testament to engineering that achieved resilience beyond even military expectations, reshaping our understanding of durability against warfare. As we inch closer to our final 3, let's discuss the Pruitt-Igoe Towers in St. Louis, Missouri. Once considered a modernist ideal for urban living, these structures fell into disrepair from the 1950s onward and faced demolition in the 1970s. Engineers found themselves baffled when they discovered that the towers, built with sheer concrete walls meant to embrace low maintenance, resisted demolition as they were filled with historical significance. The team employed explosives, yet a stalemate ensued as the structures refused to collapse. While they had implemented various demolition techniques, none proved successful against the enormous weight of the concrete. This situation illuminated a common misconception about urban demolition. While the human process aims to eradicate architectural mistakes, the very materials we use, and their inherent durability, can defy our intentions entirely. Eventually, over the span of several months, crews managed to dismantle the towers, but each section proved to be a challenge, stemming from an unexpected industrial strength. Now, let's shift our focus to our penultimate entry, the Sears Center cooling towers in Illinois. Spanning over 200 feet in height, these cooling towers were designed to house vast amounts of water, cooling systems for power plants that would eventually be deemed redundant. When the decision came to ultimately demolish the site, the engineers had to rethink their approach as conventional methods simply weren't doing the trick. In a surprising twist, they learned that the tower's cylindrical shapes and thick concrete walls formed a perfect resistance against explosive demolition. The first tactical explosions did nothing more than shatter the outer concrete layer. More explosives were needed just to chip away the surface, and in the end, nearly 1,000 pounds of explosives were required to secure a sufficient collapse, highlighting once again how solid structures can often exceed initial expectations, creating even more laborious efforts in their dismantlement. Building to our final two structures, we come to Ibrox Stadium, located in Glasgow, Scotland. Known for its iconic terracing system, it was built to hold over 50,000 spectators. The terracing has garnered a reputation for durability, remaining an iconic aspect of the football culture. During a planned demolition in the early 2000s, engineers were entirely perplexed when they struggled to bring down a section with even a few carefully placed explosives. What many may not realize is that its design incorporated immense structural stability, allowing loads to spread across the ground effectively. The deep foundations anchored into bedrock enabled it to endure intense seismic events, leading to the eventual realization that the stadium, once targeted for demolition, remained a considerable architectural challenge, known for its capacity to withstand tremendous forces, both human and natural. Finally, we arrive at the most formidable structure on our list, Soviet-era bridge pylons in Ukraine. These concrete towers were built with astonishing precision, reaching heights of over 40 meters and engineered to bear the immense loads of train traffic passing overhead. In a stunning display of resilience, when they attempted to dismantle these pylons, engineers faced surprising resistance. The materials used for construction were notably dense and well reinforced with steel rebar, allowing them to withstand seismic forces of over 7 on the Richter scale. The demolition crew was astonished. Initial attempts barely scratched the concrete. After weeks of planning, they resorted to employing advanced cutting techniques, including wire sawing and controlled blasting, to finally bring them down. This highlighted the stark lesson of material engineering: structures meant for durability often resist destruction to a mesmerizing extent. As we conclude this exploration of remarkable structures that defied expectations, we reflect upon engineering ingenuity, built from the past yet persistently present in our lives. Every structure carries within it the wisdom of design and the possibility of durability, awaiting the moment we might need them to stand firm in the face of adversity. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you. As we delve deeper, we find a fascinating mechanism that binds these resilient structures together: the remarkable evolution of construction techniques. The elements of engineering that often remain invisible to the naked eye, yet play a critical role in a structure's fortitude, are materials and geometry. These factors combine to produce outcomes that often run counter to our intuitive expectations. Consider the iconic Sydney Harbour Bridge in Australia. Upon its completion in 1932, this engineering marvel was deemed a triumph of modern design. Spanning over 1,100 meters, the bridge's arch is made of steel and weighs roughly 52,000 tons. When demolition engineers contemplated the fate of the bridge decades later, they were astonished at the thought of its resilience. However, instead of employing explosives, they reached an agreement to maintain the structure. The realization came that the bridge served not only as an essential transportation link but also as a symbol of national pride. Once again, the fear of demolition was replaced by the respect for endurance. It stood resolute, testifying to the lesson that sometimes, preserving a structure speaks volumes more than destruction. Now, let's shift gears and examine another robust indicator of engineering resilience, the infamous Hoover Dam. Completed in 1936, its immense concrete dome structure towers over 200 feet above the Colorado River. This marvel of engineering weighs about 6 million tons and is designed to resist staggering pressures, withstanding forces emanating from both water and geological activity. When faced with the daunting prospect of a controlled demolition in the wake of advancements in material testing, experts found the design itself inherently protected the dam. It incorporates a unique arch-gravity design that channels the weight of the dam into the canyon walls, giving it unparalleled stability against seismic shocks and water pressure. When engineers conducted tests exploring the possibility of partial demolition for reconstruction, they were baffled when even the most advanced explosives barely affected the dam. The structural integrity of the Hoover Dam reinforced an understanding of how effectively materials can distribute weight and resist failure under stress. In this case, the dam served both its original purpose and stood testament to the foresight of engineers who valued longevity over short-term solutions. Next, we find ourselves in the urban landscape of Boston, Massachusetts, home to the infamous Big Dig project. This massive undertaking was aimed at relieving congestion along the city's roadways and involved extensive tunneling below Boston streets. However, what makes the Big Dig notable isn't solely its engineering feats but its failures, specifically, the demolition of structures that were once deemed redundant. The elevated central artery, a central part of the city's earlier layout, was dismantled. Engineers soon discovered that connecting bridges were not as willing to yield as expected. The demolitions relied on hydraulic shears to cut through, but the steel used was impervious to traditional methods. Crews were left incredulous as the equipment struggled even to make a dent. It became clear that these structures had been built for longevity, constructed with high-strength steel that was supposed to last decades longer than anticipated. In the end, it took unconventional methods and even weeks of replanning to finally dismantle these once essential roadways, reminding us that what we deem obsolete may not always comply with our intentions. Up next, we consider the situation of the Messina Power Plant in New York. This hydroelectric dam, built in the late 1950s, exemplifies the robust design typically seen in modern energy infrastructures. The facility comprises a series of thick-walled concrete sections that are designed to withstand both hydrostatic pressures and earthquake loads. Engineers faced resistance when executing demolition plans at the plant, owing to unfurled design features that exceeded expectations. The demolition efforts initially involved chiseling away at the concrete, a laborious process that yielded minuscule results. It wasn't until workers began employing thermic cutting techniques, using high-temperature jets to vaporize the concrete, that they witnessed progress. What initially seemed like an obstacle transformed into a lesson in persistence, revealing that structures built from concrete reinforced with steel rebar make an ingenious combination against the forces of time and human intervention. Drawing nearer to the conclusion of our exploration, we turn to yet another example, the formidable underpinnings of the Berlin Wall. When the wall was put in place in 1961, it was ostensibly a temporary measure. However, the techniques used in its construction ensured an unexpected resilience. Reinforced with concrete and substantial steel bars, the wall stood tall amidst geopolitical tensions until its iconic fall in 1989. Even then, efforts to demolish segments were met with cumbersome challenges. When the decision came to bring down portions, demolition experts estimated explosive charges would induce swift results, yet the reality proved harshly different. As explosives detonated, they produced noise levels that belied the minimal visual disruption. The wall held its ground stubbornly. Subsequent attempts required heavy machinery for months until it was finally reduced to rubble. Here, the strategies and material choices exposed the misconception that demolishing a temporary structure is straightforward. It turned into yet another battle of human ingenuity versus material strength. Let us not overlook the monumental strategy seen at the Bay Bridge in San Francisco. When sections of the bridge needed replacement after the earthquake in 1989, discussions leaned towards large-scale demolition. However, Once experts began precision analyses of the structural support, their findings revealed that the arches and towers composed of dense reinforced concrete resisted forces associated with seismic activity far beyond what their original design anticipated. Ultimately, instead of demolishing, rehabilitation ensued, a testament to the integrity of design that transformed perceptions regarding urban infrastructure replacement. Lastly, we arrive at a striking and often overlooked example, the Castillo de San Marcos in St. Augustine, Florida. Built in the late 17th century as a fortress, the structure is composed of coquina, a limestone made of compressed shells. The fort has resisted both weathering and conflict across the centuries. Engineers were astonished when they considered demolishing a section to modernize frameworks. It proved completely undemolishable. Instead of crumbling under strategic explosives, it absorbed the force much like a sponge, teaching us that the right blend of materials influences durability in profound and unexpected ways. As we wrap up this odyssey through these marvels, we find ourselves reflecting on the ingenuity and resilience of human design. Whether through robust materials, clever geometry, or innovative techniques, the structures around us often tell a story of strength, patience, and the complex relationship between our aspirations and the realities of engineering. The lessons gleaned from these resilient structures encourage us to respect what stands tall, the visible megastructures that underline our existence and the many hidden engineering feats ensuring our cities endure the tests of time. The bigger the machine, the simpler the trick that makes it work.